Aloha and welcome to our video on the properties of stars. In this video, we'll describe what astronomers can learn by studying star properties. We'll explain how distance affects parallax. We'll list the factors that determine a star's apparent magnitude. And finally, we'll describe the relationship shown on a Hertzsprung-Russell diagram. Okay, so if we take a look at this picture here, what we're looking at is a picture of the constellation of Orion. Now what they did is they took the stars, the brightest stars in the sky, and they grouped them together and formed a picture, and they called those pictures constellations. And most of them are going to have a story associated with them so that we could share that story. So this is what people would talk about before TV and radio and things of that nature. Now Orion's kind of an interesting constellation. It has the belt that everybody's familiar with, the three stars here. Alnitak, Alnilam, and Mintaka make up those three. We also have a couple other stars of note. We have Betelgeuse over here, and then we have Rigel, which are the two brighter stars in the constellation. We also have Saiph, which makes up the other knee, and then Bellatrix. So you can see that we have our stars. The bigger ones will have names. Other ones will be named after the constellation they're in. Now, constellations in modern time aren't necessarily these pictures, although we still know them, but instead they represent like what you would see in that red line, and that is an area of the sky. Now when you look out into space and you see the stars, we're going to see a bunch of different things. This is what we tend to think that it's going to be like, a bunch of individual points of light here. But we'll notice that we also have these clouds, and these are nebulas, and these are where our stars are actually formed. So we can see those out there, these clouds out, when we have a better telescope or a better picture that we can take from, like, say, the Hubble Space Telescope. But this gives us an idea of what it is that we're actually out there and looking at in our night sky. Now, how big is a star? That's one of the interesting things that we have to figure out. What we noticed is there are these binary star systems. Okay, so binary means two and then star system. So we had two stars that were out there. And by looking at how these two stars interacted with each other, we were starting to be able to put together the different masses that a star could be. We found out that if we have a yellow star, which is going to be roughly the size like our sun, if it's with another one, then we notice that we have two relatively equal orbital paths of these two stars interacting with each other. However, if we have a system where we have one star that's going to be more massive than the other one, then we'll notice that their orbital paths are going to be a little bit different as such. We'll notice the one with the bigger mass is going to be a lot smaller. The one with the smaller mass will have a much larger orbital area. So this gave us a clue so we could start figuring out relative masses of stars. So the earliest way that we could find how far the stars were was by using this idea of parallax. And what parallax is it's an apparent shift of the background. So real quickly, if what we do, have you sit there, what I want you to do is hold your arm out in front of you and lift up your thumb like you're giving somebody a thumbs up. Close one eye and place your thumb over an object that's in the distance, and then switch eyes. And when you switch eyes, like close the other eye and open the eye that was shut, you'll see an apparent shift of the object. So it'll look like it's moved. You could measure that distance, and that would give you an idea of this angle. Okay, so through a lot of math, you can find this parallax angle that we see right here. Then if I extend this line straight from the star to the sun, and then come over to where the Earth is here, what it does is it gives us a right triangle, and then we can calculate what the distance is from us or from the sun to that star. Now this only works because we have this huge change in position. Your eyes only work a little bit. They're close together. But if you look here, if we took a picture of a star in the summer and then took it 6 months later in the winter, then what we'd notice is we have this big area, and we know this distance here. So because we know this distance, we can calculate this one as long as we know this angle. Now the idea of parallax isn't new. The ancient Greeks tried to do this to prove that the sun was in the center of the solar system, but unfortunately the equipment they had, they didn't have telescopes, so they weren't able to take accurate enough measurements to use this. Parallax is really good for measuring close stars, but it doesn't work too well with further away stars. Okay, so let's talk about brightness of a star. We call the brightness of a star its magnitude. And magnitude is kind of interesting. If we have a positive number, that's going to mean that it is going to be dimmer than those that have a negative number, which are going to be brighter. So the more negative the number is, or the smaller and more negative it becomes, the brighter that star is going to be. So we have that one, we can look at it that way, and that's how we rate our stars. So if you go back to Hipparchus did his star catalog, and he cataloged probably about 500 stars that he could see, and we still kind of use the same type of method that he did, because looking at brightness hasn't changed a whole lot for most of our stars. Now when we talk about magnitude, we have two different kinds of magnitude. We have what we call apparent magnitude, and then we have what we call absolute magnitude. Apparent magnitude is how bright is it from Earth. When we look at it, what's its apparent brightness? And we'll notice that if we take the brightest object in the sky and the brightest star that we see, the sun, it has an apparent magnitude of negative 26.7. So that's going to be really super bright. The closest star has an apparent magnitude of 0, and one of our brightest stars is going to be Sirius. Okay, and Sirius has a magnitude of negative 1.4. So these are apparent. This is when we're looking at the stars, how bright do they seem from Earth. Then we have absolute magnitude. And absolute magnitude would be as if we took all the stars and we put them at the same distance away, how bright would they be in relative to each other? And this is where we start to see some interesting things. The sun, that was a minus 26 in apparent, its absolute is a 5. So it's going to be kind of a dim star. It's only an average star that's out there. Alpha Centauri is going to be a 4. Sirius is going to be a 1.5. But take a look at some of these others. When you go out and looked at Orion and saw Betelgeuse, notice it was only a 0.8. So it was not a super bright star, but it wasn't very dim either. It's just kind of there in the middle. But notice when we have its absolute magnitude, it's going to be a lot brighter. And if we take one like Deneb, who is so far away that its apparent magnitude is a 1.3, its absolute is in 6.9. So we know it's a much bigger, brighter star, but because it's so far away, it appears to be a dimmer star. So even though you can look in the night sky and see two stars that look to be about the same brightness, because their distance from Earth is going to vary, B is going to look a lot brighter because it's closer. A is going to look not quite so bright because it's so much further away. So when we talk about magnitude of stars, apparent is what we see, absolute is if we put them at a distance. And it's important that we know the difference between those two types of magnitude. Okay, in this picture we have probably the most important diagram when it comes to stars, and that's the Hertzsprung-Russell diagram here. And we're going to talk about it, but I'm actually going to use a different one than the one we have in the lessons. So let's go to that one and I'll explain our way around the Hertzsprung-Russell diagram. Okay, so here we have a different picture of the Hertzsprung-Russell diagram, and there's a couple things I want you to see. First of all, what we're going to have is our surface temperature of the stars down here. And what you'll notice that makes this one a little bit unique is we have 3,000 kelvins here, but we're going to have 30,000 kelvins here. So it actually gets hotter the closer we get this way, and it's going to cool off a little bit as we travel down this way. Now, we can name our stars or classify our stars by temperature, and you can see this M through O classification. M are going to be the cooler ones, and then we'll go to K, G, F, A, B, and then O here, which are going to be our brighter stars. Now, on the other axis, we generally omit luminosity. How bright is it? And we measure that in solar units. So if we find our one luminosity, that's going to be one sol, and we'll notice it right here is where our sun is. So our sun is a yellow star. It's a G class. It's going to be about 5,500 kelvins warm, and it's going to have a luminosity of 1, which would make sense if we're measuring it against the sun. Now we can see there's different regions. We also have sizes. You can see here we have 0.1 solar radius, here we have 1 solar radius. So you can see that a star on this line here, so if we go down here and we look at Proxima Centauri, which is right here, we'll see that that star is going to be about the 10th of the size of our sun. If we go up a little bit more, we have our 10 solar masses here. Here we have our 100 solar masses, and we even have 1,000 solar masses. So if we look at Betelgeuse, Betelgeuse is going to be about 1,000 times the size of our sun, just in the radius part there. So we can see that stars are going to get a lot bigger. Now, we have our small little red stars that are going to be over here, and these ones have been burning for a while, and we'll talk about that in the next video. We have what we call our main sequence, and these are stars that are doing what they should be doing at this point in time, converting hydrogen into helium for the most part. We have different groups on here. we're going to have our giant stars here, which we could see in Aldebaran and Arcturus. We'll have our supergiants, and this is where we get Deneb and Betelgeuse. And then, like I said, we have our main sequence, which is going to run up through the middle part here. And then down here, we have our little dwarf stars. Okay, and these are going to be a lot smaller stars. Okay, in fact, they're going to be 100th the size of our sun. So the HR diagram can give us an idea. When we plot these, we can figure out by looking at the color of the star, we can figure out how hot or how cool the star is burning. We can know by distance about how big they are. So it gives us a lot of detailed information on stars. Now there are a couple other things I want to show you some pictures of that we have out there. The first are going to be Cepheid variable stars, and Cepheid variable stars are stars that are going to vary in brightness. So if we look at this star here, okay, it's the Cepheid variable in galaxy M100, notice that it's going to go from being really bright to getting kind of dim, and then it's going to brighten up again. So what's going to happen is this star is going to kind of pulse in its brightness. It's going to go bright and dim over the period of a couple days. So these are variable stars. They help us figure out distances for the stars that are going to be a little bit further away. Some of the other things we want to talk about a little bit more in the lessons are here we have a supernova, okay? And this is when a star explodes, and we'll talk about that in our next video. And also we can look out and we can see some things like nebula here, and this is the Horsehead Nebula, and you can see why it gets its name. Okay, that's it for our video. Sorry this one was a little bit long. Good luck on your quiz, and we'll see you in the next video. Aloha and welcome to our video on stellar evolution. In this video we'll identify which stage marks the birth of a star, we'll explain why stars eventually die, and we'll list the possible stages of a star's life cycle. Okay, so here what we have is a picture showing the life cycles of a star, and what we're going to do is we're going to start off with our dust and gases forming our nebula here. So this is going to be our first stage. Now gravity is going to pull this dust and gases together, and it's going to continue to do so, and it'll get larger and larger, and you'll have more and more mass coming together. And ultimately what's going to happen is you're going to have a protostar occur, and a protostar is where you start seeing nuclear reactions will start to fire. It gets hotter. You can see this separation from the rest of this dust and gas cloud. So there's an actual difference there. Once that happens, it's going to continue down. The protostar, you're going to see this isolation. It's going to continue to squish a little bit more. And then we reach this equilibrium of forces, and that's when we have the birth of our main sequence stars here. Now our main sequence star is going to take the rest of this hydrogen and it's going to convert it to helium. And then when that runs out, what's going to happen is you're going to have less explosion on that star. So it's going to want to compress down a little bit more. And as it does so, it'll do so until it starts to convert helium. And once it converts that helium or burns that helium and makes the larger elements, once that occurs, we explode upwards in size and get into our giant stage here. Now our giant stage is going to use up this helium that it's burning, and then when that helium burns up, then we get this compression again, and then depending on the mass of the star is where it's going to end up. So here we're going to go through a variable stage. Eventually we'll flare out and form a planetary nebula stage. We may go to a white dwarf, and ultimately the white dwarf will cool off to a black dwarf star there. So we talked about these nebulas as being the birthplace of stars, and here we have these nebula, and you can see the gases and the dust clouds that are there. And what's going to happen is that's going to compress down, and it'll form a protostar stage. And then once that protostar stage compresses a little bit more, we get to these equal balanced forces. That's when we have our birth of a star. So here we can see probably a star here. We'll see a couple stars over in here as well. But you'll see that this is where our birthplace of stars occurs. Now, when we're talking balanced forces, what we're looking at is we're looking at a balance of gravity, which we'll see in blue here, compressing and pulling all of this stuff towards the center. So gravity is going to be working this way, and then we'll have this gaseous radiative pressure here from this explosion inside that's going to be forcing it out. So when they equal, then we end up with a main sequence star that's going to be about the same size for a while as it's burning. And that's where our sun is. Our sun's not going to change size an awful lot right now. When it runs out of hydrogen, it'll compress down, and then when it converts to helium, because it's a bigger reaction, it'll actually expand the size of the sun that way. So once again, looking at our life cycle, we see that we have this gas and dust cloud, and we're going to have gravity pulling it in this way. And that gravity is going to do so until we get to about this stage here where we have the protostar. And in the protostar, we see a little bit of light coming from there, but we're going to experience some expansion and contraction of that star. So in this protostar stage, we're going to have a small star, then it'll explode out to a larger star, then back to a small star, back to a larger star, and it'll kind of level itself out until these forces balance. When that happens, we get a main sequence star right here. Okay, so that's like the birth of a star right in that area. And then we'll kind of travel through our giant phase, and like we said, we'll peter out. And it kind of varies on the mass of a star. That's the big determining factor. Okay, so let's begin and look at a low mass star. Now, a low mass star is going to start off as a nebula, which we see here, and it's going to compress down through the protostar stage and form this main sequence star. Now, because it's low mass, that means that it's going to use its fuel at a low rate, and because it's using it at a low rate, they're going to have these long lifespans. And in fact, we have some of these stars that are burning, and we think they may have started right after the Big Bang. So they've been burning for about 12 billion years, and they're still burning through. Now, what we notice is over time, they're going to use this hydrogen up, and as they use this hydrogen up, these balanced forces aren't going to remain that way, so it'll compress down to a white dwarf, where we'll still see some light being produced, and we can see some of these out in the universe. And then we think that it'll cool further and form what we call a black dwarf. And a black dwarf is just going to be a burnt out star, but we don't see any of these because we don't think that the universe is old enough for any of these to occur yet because of this low rate of burning that we see in these low mass stars. Now, if we look at a medium mass star, and that's going to be kind of like our sun here, what we'll notice is it starts off as a nebula here, and then we're going to compress down through the protostar, form our main sequence stage, and it's going to burn a little bit faster because there's more mass, and it'll actually come down, and when it runs out of hydrogen, it'll compress down and we form this red giant stage. Now, a medium mass star is going to burn through the helium, and it burns through the helium a little faster than the hydrogen. And what will happen is with a medium mass star, we end up with a planetary nebula. So when the red giant goes, it'll compress down, and then it'll kind of like fizzle out to a planetary nebula. And from there, in the middle, we'll have our white dwarf formation, and then ultimately we can go to a black dwarf this way as well. Okay, so now let's take a look at massive stars. Massive stars have so much mass that they're going to burn through their material quicker, so they have a much shorter lifespan. So when we compare like a low mass star's lifespan, where it may be longer than the universe has been around, a massive star is going to have a much shorter lifespan, comparatively speaking. Now, these guys also start off as a nebula. You're going to have this contraction through the protostar till we get to the main sequence stage, and then it's going to burn through the hydrogen a little bit faster because of its massive size. When this happens, it'll explode, but instead of forming a red giant, it'll form what we call a red supergiant. And a red supergiant example would be like Betelgeuse in the constellation Orion. Now, this will burn through the helium, and it'll make the heavier elements, and then once it runs out, it'll compress down again, and then we'll have this violent supernova explosion. So we'll look out into the sky and we'll see this star just go super bright. Some of these are bright enough that they've been reported seen during the daytime. So we haven't had one that bright in hundreds of years, but Betelgeuse could go at any moment. So we might have the opportunity in our lifetime to see these. Okay? Then this supernova, depending on the size of the star, will compress down into what we call a neutron star, or it might even continue to compress down a little bit further all the way to a black hole. So now when we look at our picture of the life cycle of a star, what we're looking at is that of a medium mass star. And you can tell that by noticing the planetary nebula stage here, the white dwarf, and ultimately the black dwarf stage. And if you look at this, this kind of looks a lot like our HR diagram, where we have our main sequence coming through here. We're going to have magnitude or luminosity on the size here, and our surface temperature here, where we have our 3000s to our 30,000. So you can see how the HR diagram we showed you, there was this main sequence here, we had our giants up in here, and then we had our little dwarf stars down here. So you can see how it shows that the HR diagram kind of depicts this evolution of the stars. So in this chart that you'll see in the lesson, this is the key here, this initial mass of it. What's going to happen is if the sun is 1, so a star like our sun, its main sequence is yellow, which is what we see, it will have a red giant phase. After the giant phase, it'll go into a planetary nebula stage, and then ultimately we'll end up with a white dwarf. If we get a larger star, like 6 times the mass of our sun, then we have a white burning star. It also has the giant phase. It's going to go supernova, but then it'll compress down to a neutron star. And a neutron star is the densest thing that we can see or we can record in the universe. If we go more massive, like 20 times our sun, then we have a blue star, so something like Deneb that we saw earlier. It'll have a supergiant phase here. It goes supernova, and then ultimately it can become a black hole here. So our black holes are going to be the results of these supermassive stars, these 20 times the size of our sun. So what is a black hole? Well, a black hole is going to be an object in space, and we call it a singularity, which means that we're taking an entire star and we're compressing it down into the size of a dot, of an infinitesimally small little dot. And that's what we call a singularity. It's going to have such high density that it's going to create a gravity around it that you're going to have what we call an event horizon. So our singularity is here, and then we're going to have this boundary around it that we call the event horizon. And anything inside of the event horizon will be pulled into this singularity. So light itself cannot escape from this one. And a lot of times around this event horizon, we have what we call an accretion disk, and you'll see this orbiting disk here in the picture. And that's what they're talking about, this one right here. This black hole is actually, the accretion disk is pulling off from a red giant. So it was probably a binary star system. One of them collapsed down to a black hole, and you can see that mass is being pulled from this red giant down into this accretion disk here, where it will ultimately fall into that singularity, and that'll only cause the black hole to get a little bit larger. Now, black holes are also interesting because we've hypothesized that at the center of the galaxy is a supermassive black hole, and that's what causes the galaxy to be rotating as we see it. And we'll talk about that a little bit more in the next video. For now, enjoy the lesson and good luck on your quiz, and we'll see you in the next video. Aloha and welcome to our video on the universe. In this video, we'll describe the size and structure of the Milky Way galaxy. We'll list the ways in which galaxies differ from one another. We'll cite the evidence that indicates the universe is expanding, and finally we'll describe how the universe began according to the Big Bang Theory. Okay, so here we see an artistic interpretation of what the Milky Way galaxy could look like. It is a spiral galaxy, so you notice we have the center of the galaxy here, and then these arms are kind of spiraling out from that. We'll see that the sun is here, and it's located on the Orion arm of the Milky Way galaxy. Looking in towards the Milky Way, what we'll notice is in the summer sky, when Sagittarius is in the sky, we're looking across through Sagittarius towards the center of the Milky Way. So what that means is in the summertime, if you went out and you looked for the teapot, which is Sagittarius here, coming out of the teapot like a bunch of steam is the Milky Way galaxy, and back in here is where we would find the center of the galaxy. In the wintertime, when you see the galaxy, what we're looking at is we're looking outwards, so it's not going to be as bright as it is in the summertime. So this gives us a clue as to what the galaxy is going to look like. Now, coming in towards the middle, in the center of the galaxy currently we believe is a supermassive black hole. And that supermassive black hole would be in the realm of where we see that constellation Sagittarius. So that's kind of what our Milky Way galaxy would look like if we could take off on a rocket ship and go out and look back at the galaxy. But we'll see the problem with doing that. Now, we've talked about Sir Edwin Hubble a little bit earlier in this course. Hubble returns to us when we start talking about types of galaxies. We have 3 normal types of galaxies. These are our ellipticals, our normal spirals, and then we also have a barred spiral galaxy. And this is what Hubble classified these different galaxies. There's a 4th type of galaxy. Sometimes we link the spirals together and say there's 3 types, and that would be an irregular galaxy. Now, elliptical galaxies are going to be kind of elliptical in nature. If it's an E0, you'll see that it's almost spherical here, but as we move higher in the numbers, we'll see that it gets stretched out a little bit more elliptical. Then we get to our spiral galaxies. Now notice the ellipticals are going to be all uniform in color. They tend to be kind of orangish, yellowish. That's the elliptical color. They're made primarily of older stars. Now here we have our initial spiral, and you'll notice that the center of the spiral galaxies are going to have these older stars, but as we travel outwards, we're getting these bigger, brighter blue stars, which are going to be younger, shorter lived stars. Okay, so that's some way that we can look at the difference in the color, and it gives us an idea of what's going on, and we kind of covered that a little bit in stellar evolution. Our normal spirals, you can see we have an A here, and they'll go up to a C, where we can see the arms are spread out and really spirally. Now the barred spirals, what we notice is it has this little like bar here extending out. And so we generally have fewer arms. Here we can have a very pronounced bar, and you can see this bar coming out, and then we'll have the spiral arms coming this way. Okay, so this is how we classify our galaxies that we can see. Now here we'll see some other pictures. Notice we have a regular spiral galaxy here and here, but here we have what we would call a barred spiral galaxy, and you can see that bar projecting out. Notice the color. Notice how we have the more oranges and yellows in here, and outside we're going to have these bluer colored stars, these brighter stars here as well. Elliptical are just going to be this large globs, and they vary in size. The biggest ones can be elliptical, and the smallest ones tend to be elliptical. And then we can see it stretched out into a more oval shape here as well. And then we have our irregular galaxies here, and they don't have any obvious shape. So there's talk about how we can have galaxy evolutions, but we're just going to look at different types of galaxies here. And most of these we've gotten from our Hubble Space Telescope, that we looked out and we could see all these different types of galaxies. So in the next couple of slides, what I want to do is I want to show you just a little bit about size in the universe. So we can kind of get an idea of size there. So here what we see is the Earth. Okay, and that's a good starting place. We know how big the Earth is. We can travel around it. We see it that way. If we extend out a bit, we get to see our solar system. So we can still see where the Earth is in the sun, but this would take us to our entire solar system. Notice we get all the way out to the Kuiper Belt. We see that Earth is here, but we can't really see it, but we can still see our sun right there. So now if we go out to another level of organization, we get to our interstellar neighborhood. So we have the solar system is here, okay? Our sun is right here, so we can still see where the sun is, and these are going to be the stars that are closest to us. Things like Arcturus is here, Pollux is here, Aldebaran is here, Castor is here, Vega is here. So we can see some of the stars that are going to be nearby. So these would be our closer stars, our closer proximity ones. Going out a little further, we get to the Milky Way. And we'll notice that here we're showing where the solar system is. That would be on the Orion arm. And we can see how big it is. And now there's no way we can tell the difference of where our sun is or where our solar system is. We just kind of know its approximate location. Going out a little further, we get to our local galactic group. So here's the Milky Way galaxy here. We can still see it. We have the Sagittarius dwarf over here, and our bunch of dwarf galaxies you can see are surrounding us here. Okay, so this is where our Milky Way is. We also have the Andromeda galaxy here. And one of the interesting things is we'll talk about how everything in the universe is kind of moving away, but the Andromeda galaxy is coming closer to us. So there's a chance that we'll collide with them, but it won't be for a couple billion years, so I think we're safe. Now, that takes us out to our first supercluster. So we have our local galactic group here, and then looking in, we see the Virgo cluster here. Notice the Virgo cluster is going to be bigger than our local galactic group. So when we join these two clusters together, we get a supercluster, and that's going to be what we call the Virgo supercluster, named after the largest group, which is that Virgo cluster again. So taking another step back, here's our Virgo supercluster here in the middle. And notice what we're doing is we are joining in with these other big superclusters. The Hercules one here, Ophiuchus up there, Ursa Major over here, which is a large one, the Sculptor supercluster there. So we can see when we come back, there's a whole bunch of superclusters. Now, taking a step further, here's our local supercluster, the Virgo supercluster. Now we really lose track of where it is. And this gives us the observable universe. Key part is observable. So what that means is if we're in the center going outwards, we can go out about 13.6 billion years. 13.6 billion light years away is the edge of the visible, the observable universe. That's not how big the entire universe could be, but this is as big as it could be that we can see it. That's why we call it the observable universe. Okay, so let's revisit what Hubble told us about redshift. What he said is if we have an object that emits light that's moving away from us, it's going to stretch the wavelengths out apparently, and that's going to give us a kind of shift to the red in color. So because of that, when we look at these distant galaxies, we can see that they have this redshift, and what it means is that if our sun is here, all these galaxies are moving away from us. And the only way to explain that they talk about is to use the idea of like a loaf of bread with raisins in it. And what we notice is when you have the lump of dough here and there's raisins in there, when that bread expands, the distance between the raisins is going to expand as well. So that's how we say that the universe is expanding, by looking at the redshift of all these galaxies around us. So what is this Big Bang Theory that we hear about? Well, here's a real simple thing. 13.7 years ago, there was a Big Bang that occurred, and that created our universe. Now, in the first couple minutes of that, we had rapid expansion, cooling, we had the formation of the stars. Notice that the first stars and galaxies formed about 200 million years after the Big Bang. So there was a lot going on the atomic level in those first couple seconds and minutes, and it took about 200 million years for the first stars and galaxies to form. Now, the solar system formed, we think, about 4.6 billion years ago, and that'll lead us all the way up into today. So let's take another picture of it and we'll see it a little bit better. So let's explore the Big Bang Theory a little bit more. We have the Big Bang started here where time begins. And then in this first 10 to the minus 43 seconds, so that means it would be a minuscule amount of time, the cosmos goes through this super fast inflation. So it expanded from what we think was the size of an atom to that of a grapefruit in only this tiny amount of time. In the next 10 to the minus 32 seconds, we see here, this post-inflation, the universe is a seething hot soup of electrons, quarks, and other particles. So we see that kind of down in here where we see all these tiny little things. In the next 10 to the minus 6 seconds, we're going to see a rapid cooling. The cosmos prevents quarks to clump together into protons and neutrons. So now we saw electrons forming here, and here we're seeing the formation of protons and neutrons. And that takes us to about 1 second after the Big Bang. In the next 3 minutes, it's still too hot to form into atoms, but these charged electrons and protons prevent light from shining, and the universe is a super hot, kind of foggy looking environment. In the next 300,000 years, electrons are combined with protons and neutrons to form atoms, and this is going to be mostly hydrogen and helium. And it's here that we can actually now see light shining. So it takes about 300,000 for that to occur. In the first billion years, gravity is going to make these hydrogen and helium gas coalesce to form these giant clouds that will become galaxies and stars, and we'll see these nebula basically forming. And after about 15 billion years, our galaxies cluster together under gravity. These first stars are starting to die. Heavy elements are thrown out into space. And this is how we get into our present day. So it all started with this little bang, and then we saw a lot of expansion here in the first second. And that's what allowed us to form atoms. And then as we see as it goes on, we got to form what we see as our modern day universe. Okay. Well, that's just about everything for our video today. Good luck on your quiz, and as always, we'll see you in the next video. Bazinga! This is our last video, so good luck on your review test, and I hope you enjoyed the course.